All right, I realize that Dr. Sen started this chapter with you guys, but I have really specific things with chapter 4 that I like my students to know, so I'm just going to start from ground zero, if that's okay with you guys. Okay, all right. Just to make sure, so that my later class didn't have just Dr. Sen doing this, and I want to read it. Okay. Aqueous reaction solutions go down to this line of the tea. I like chapter 4 and chapter 5, it's all math. But I really like aqueous reactions and solutions stoichiometry because I am a quantity chemist. Solutions and analytical systems are my specialty as chemists. We all decide as undergrads what branch we want to specialize in. Some people are organic chemistry or biochemistry or physical or analytical. I like solutions and water systems. Prior to getting a job as my first teaching job, I actually got an offer from Palo Verde Nuclear Plant because they need people who are chemical water chemists, that would be my job, to come in and look at the water and they put through the nuclear plant as a coolant because they put a lot of things and they test the water all different processes. So I love aqueous reactions and solution stoichiometry. Like I said, this is my cup of tea. This whole chapter is stuff I like to talk about. Dissociation is the first thing. Remember the animation that I showed you in, I think it was chapter 2 or 3, where it showed ionic salts. Anything that's ionic is a metal-metal combination. You put it in the water, and this idea of dissociation is the fact that it comes apart, right? And we call the ability of an ionic substance to dissociate when we put it in water its solubility, right? Solubility means a different thing to chemists than it does to everyday people in the general population. Solubility to a chemist means that when you put something in water, it's going to dissociate, right? You talk to an everyday person, and they go, oh, well, sugar is soluble, right? You go, well, yeah, it's soluble, it dissolves in water, but it doesn't dissociate. There's only certain things that will dissociate. In this class, we talk about solubility as being bimodal. Either it dissociates and dissolves, or it doesn't, right? It's either one of two choices. It's either soluble or not soluble. When you get to Chem 152, then your perspective changes. You take the things that in this class we say are not soluble, and you discover that they have a tiny little bit of solubility that varies depending on a lot of conditions. And you use that tiny little bit of solubility, you describe it using a lot of mathematics. Okay? So I don't want you to think I'm lying to you. If you take me in Chem 152 and you go, hey, wait a minute, I thought everything was either soluble or not soluble, right? That's how we talk about it in this class. But when you get to 152, you look at the things that are not soluble and their tiny little degree of solubility based on some numerical examples. Okay, so solubility and dissociation are linked. This idea of something being soluble is this dissociation idea. There's a nice link. We did already look at this link before, and it showed, remember, the salt crystal falling into the water and the water molecules taking the pieces, the ions of sodium and the ions of chlorine off of the salt crystal. When we discuss solutions in this class, solutions are the basic definition in our flowchart example of what a solution is that it's a homogeneous mixture of two or more pure substances, right? So, for example, if I wanted to make a solution of salt and water, I would have two vocabulary words that I would have to use to describe the solution of the salt and the water. Those vocabulary words I would use are specific when we're describing concentration values. All right? So to look at this idea of concentration as an expression of how much solute we have in a particular solvent. So these are two vocabulary words we're going to be using a lot in Chapter 4, and we're going to use them in the context of calculations that describe concentration, because chemists have so many different ways of measuring volume, right? We have resonant cylinder, we have beakers, we have flasks, we have pipettes and burettes. We have lots of different ways of measuring concentration of those things. The solute is usually the thing being dissolved. And that thing is usually in the minority of concentration. You see those little square brackets? Chemists mean concentration of. So when you see square brackets, and so for example, if I said this, the concentration, what is the concentration of lead nitrate? Okay, that might be how you would express it. So you're going to put the little square brackets and you say concentration up. So the solute is the thing generally that's in the minority of concentration, the thing that's being dissolved. The solvent is the thing doing the dissolving. Now we're used to a good old H2O being our solvent, and they call water the universal solvent. Is good old H2O. Why do you suppose they call good old H2O the universal solvent? What might a universal solvent be capable of? Just about everything. So they call it a universal solvent because most of the substances that you might put into it are ionic. So most, not all, but most ionic substances will dissolve or are soluble in water. And that's because water is a very polar molecule. Remember, it looks sort of like Mickey Mouse. You've got two hydrogen atoms combined with an oxygen atom. And if you look at the molecular geometry of water molecule, it's got two non-bonded electrons floating around the outside. Those non-bonded electrons give this part of the water molecule an excessive negative charge, right? If you've got non-bonded electrons hanging out on one side of the molecule, it's going to make that side of the molecule negatively charged. Conversely, on the other side of the molecule, we have two hydrogen atoms. Each of those is slightly positively charged, so the water molecule is positive on one side and negative on the other. And that's what we call a polar water molecule. Batteries are also polar, right? You have a cathode and an anode. One side is positively charged, one side is negatively charged. The Earth is polar. You have the North Pole and the South Pole, right? They actually think that the Earth has changed poles in history, not recent history, since man's been alive, but there is evidence in the rock work, and geologists have to talk about this stuff, that when magma and hot rocks are solidifying, and there's iron in the magma or the hot rocks, as the magma cools, you have lava that's come out of the volcano, as the lava cools, the magnetic fields of the planet orient the iron in a certain way as it's cooling, so it points to the North Pole, right, as it cools. And if you look at it, you go, wait a minute, those little magnet fields are going the wrong way. The North Pole's supposed to be this way. No, this way, right? And pointing the opposite way. When they think that at different points in the history of the planet, the poles have changed. The north and south have changed in different ways because the polarity of the iron that has solidified in the rocks changes. So water molecules, because they are very polar, polar water will dissolve most ionic substances. And that's because ionic substances are also polar, right? Because they have a plus combined with a negative charged thing in that crystal. For example, like you have sodium chloride, right? You got repeating structure of sodium and chlorine as it goes on and on and on in a three-dimensional shape, right? So sodium and chlorine and sodium and chlorine and sodium and chlorine alternatively. All right, so solvent versus solute. An electrolyte is something that allows electricity to be conducted in a solution. In order for electricity to be conducted, for electrical current to be fluid, you got to have ions in the solution. Gatorade advertises that it's an electrolyte. If you look at the bottles, anybody have a bottle of Gatorade in here? Usually somebody will have one of Gatorade, especially when it's warm outside. Well, if you look at the back of the bottle, all of you at this point in chemistry education should start being educated consumers with respect to what you know now about chemistry. Look at the back of the package. Look at the back of a bottle of things that you're consuming and say, I know what that is. If you look at the back of a bottle of Gatorade, you'll see lots and lots of salts. There's salts of magnesium and calcium and sodium. That's why Gatorade tastes a little salty, because it has lots of salts in it. Those salts are electrolytes. They're positive and negative ions, and when they go into solution, the compound breaks up into its component ions, and that solution then electricity. We drink Gatorade or electrolytes because our cells in our body and our brain, and memory synapses in our brain require electrical to be conducted between the different cells and the circuits in our body. And if we're low on electrolytes, then our organs start to shut down because those electrical components can't transfer information from one thing to another. Right? If you get dehydrated, like you get real sick and you're throwing up a lot, well, make sure you drink some Gatorade because your electrolytes are going to be low. You're going to be feeling sluggish and not good at all because of the fact that your body is not working up to its efficient capacity because you can't conduct electricity in all the different aqueous solutions in your body. So a non-electrolyte, it may dissolve in water, but it's not going to conduct electricity. Something like sugar. What are the components of sugar? What kind of atoms are in a sugar molecule? Carbon, hydrogen, and oxygen, right? It's usually a ratio, something like this, like C11H22O11, and there's all different kinds of sugar. There's fructose, glucose, maltose, all different kinds of sucrose, lots of different kinds of sugars. Anything with an OSE on the end is a sugar. Now, when I put this in water, it will appear to dissolve, right? John Q. Public would say, oh, I know the sugar is soluble because I can put it in a hot coffee, stir it around, and it appears to disappear. But is it dissociated? No, it does not dissociate. It may dissolve, but it doesn't come apart, and that's because water is polar and sugar is non-polar. So like has to dissolve like. I like this animation. Let's see if we can get it to come up, because it shows electrolytes. Now I'm going to do the voiceover on this because they talk about stuff that we don't necessarily need to know. So there's this one. Here we go. Okay, let me make sure that the sound is off. All right, so this is what we call a conductivity apparatus. You may have seen this if you took Chem 130. One of the last experiments that we did in the class was an experiment on electrolytes. And we took a little conductivity apparatus and you dipped it in a whole bunch of solutions all around the room. And the light bulb either lit if it was an electrolyte or it didn't light if it was a non-electrolyte. All right, so we can put a solution in to this container that has the electrodes in it. The electrodes are connected to the light bulb and a power supply. And if there's ions in that solution, then the light bulb will light up. Let's see what
an electrolyte is a substance that, when dissolved in water, results in a solution that can conduct electricity. The light bulb will light if a substance is an electrolyte.
We've got a solution, and now we've got NaCl.
Sodium chloride, NaCl, is a soluble salt that is assumed to completely dissociate into ions. NaCl is a strong electrolyte when dissolved in water. The solution contains a large number of ions, and the light bulb is brightly lit. Polar water molecules interact with the positive and negative ions of the salt. The positive ends of the water molecules are attracted to the negative
and I like
chloride
this
ions.
part of it because
The
it
negative
shows
ends of the water
graphically what's happening
molecules
to
are
the
attracted to
concentration of the
positive
whole thing
sodium
that you put
ions.
in.
This interaction
The concentration
between
of
the
that
water
is
and the
doing
salt
what?
ions causes the salt to break apart.
It's shrinking
or
because the
dissolve
molecule
in water.
or the piece of salt is being consumed soluble,
Hydrofluoric
made soluble
acid
by the water.
in water.
And then let me stop it right here. And you see that the components, sodium and chloride, the concentration of those two things is increasing. If you look at the concentration of the sodium and the chloride at the very end, and then we compare that to the concentration of the sodium chloride at the beginning, can you see that the concentrations go up to the same value? So say, for example, I started with 0.3 molar of NaCl. At the end of the time when they all dissolve, at the end I'm going to have 0.3 molar of sodium ions and 0.3 molar of chloride ions. Do you see what I mean? That the concentration of the components is the same as the original when it started. All right, let's continue with the animation. Now they're going to talk next about strong versus weak acids. All right, strong versus weak acids are similar in that they either dissociate or don't dissociate. Let's go back and I'm going to show you some strong versus weak acid ideas here. All right, so strong versus weak acids. I'm going to use an example of a strong acid that you use a lot in the chem lab, which is hydrochloric acid. In fact, we used it today. And another example of an acid you're going to use a whole lot when you get to Chem 152, which is acetic acid. All right, hydrochloric is a strong acid. Acetic acid is a weak acid. The difference between a strong and a weak acid has nothing to do with their concentration. Concentration and strength of an acid are independent measures of an acid, and they don't have anything to do with each other. A strong acid simply means that it dissociates completely. Meaning every piece of HCl that I put into water is going to break up into hydrogen ions and chloride ions, both in aqueous solution. So we have 100% dissociation. Every single piece you put in water breaks up into its component ions. This is why we use what's called a completion arrow when we're describing strong acids, because these reactions go to completion. They start over here, they go all the way across, and they go to completion. Weak acids, on the other hand, and you'll get a lot more of this when you get to Chem 152, we use a different kind of arrow. We use what's called an equilibrium arrow. An equilibrium arrow means, yep, some of that stuff is going to break up into hydrogen ions and acetate, polyatomic ions, both in aqueous solution. But it's just as likely for these kind of ions to go back and become part of the original acetate. This dissociates only partially. And maybe, in weak acids, maybe 5% actually break up. So 100% break up in a strong acid, only a tiny smidgen of weak acid things actually break up. So if I looked in a container of strong acids, right? Here's my container of strong acid. In my container of strong acid, I'm going to have only hydrogen ions and chloride ions floating around. That's the only species I will have. And the ratio of hydrogen ions to chloride ions is going to be 1 to 1, right? You're going to have lots of them. But it's all going to be in a ratio of 1 to 1. I'm only going to see the ions in solution. Conversely, in a weak acid, I'm going to see a whole bunch of the undissociated acid. And only a few hydrogen ions and acetate polyatomic ions. So 95% of the stuff in the beaker is going to be the undissociated whole acid. Only about 5% dissociates. So which one of these solutions would conduct electricity better? The strong acid, where 100% dissociated, or the weak acid, where only 5% dissociated? The strong acid would be a much better electrolyte. So that means strong acids are also strong electrolytes. Strong acids are strong electrolytes. Weak acids are weak electrolytes. Strong acids, weak acids, has to do with their strength as an electrolyte, not their concentration. All right, so a strong electrolyte dissociates completely when you put it in water. A weak electrolyte only does partial dissociation. So a weak electrolyte, the light bulb would light only a little bit. It would hardly barely be illuminated. A strong electrolyte, the light bulb would light up very completely. All right, strong acids versus weak acids. You will need to identify what are strong versus weak acids not only in this class, but when you get to Chem 152. You're going to have to know both. Easy way to know it is simply memorize the 1, 2, 3, 4, 5, 6, 7 strong acids listed there. All right, let's look at some tricks to try and memorize which of the acids are the stronger ones. Look at the trend of the first 3. What are those? Where are those based on your periodic table? First 3 acids, where are those based on your periodic table? They're where? They're the halogens, right? Hydrochloric, hydrobromic, and hydroiodic are halogens. So that's a good way to remember. So see where hydrochloric, hydrobromic, and hydroiodic would be? How come hydrofluoric, how come HF is not a strong acid also, right? The other three members of the halogen family make strong acids. How come HF doesn't make a strong acid? Let's take a real quick look. Up at the periodic table there, see F is at the top of the group of the halogens? Fluorine, bromine, and iodine are right below. Yes? That's a huge part of it. We know that fluorine is the most electronegative element of all the elements on the periodic table. What does that mean, that it is very electronegative? And also, another term that you'll hear used is electron affinity. Like fluorine has a high electron affinity. Here's a comparison. I have a high affinity for dark chocolate. Especially dark chocolate that has any kind of carbon associated with it. I have a high affinity for that. What does that mean? I really like it. I'm attracted. I want to eat some of that dark chocolate. Okay. If an element has a high electron affinity, what does that mean about that element? It likes electrons, it's going to steal them from other people. It's very greedy for electrons. So fluorine is the most greedy. So it's the most greedy for electrons. What does that mean about its bond that it makes with H and F? Well, the bond is fairly strong, but it's also going to be holding electrons higher. Think about the size. Look at this. Think about the size of fluorine, chlorine, bromine, and iodine. Of those four, who's going to be the biggest atom? Fluorine, chlorine, bromine, or iodine? Iodine is going to be the biggest. Think about that. If you're the biggest atom, you're going to hold the hydrogen pretty darn far away from the nucleus, right? If you're the smallest atom, like fluorine, you're going to be holding the hydrogen atom pretty tight to the nucleus. Which one is it easier? Going to be easier to take that hydrogen ion away? If you're holding it way far away, like iodine, or if you're holding it close to you, like fluorine. It's going to be much harder to take that atom away, that hydrogen atom away, if you're fluorine, because fluorine is holding it right next to it. How many electron shells does fluorine have? 2 electron shells. How'd you know that? It's in second row, so it has 2 electron shells. That means that hydrogen is pretty close to the nucleus, which is positively charged. Positively charged, so it's going to be holding onto it pretty tightly. It's going to take a lot of effort to take fluorine off of that hydrogen. Not so much chlorine, bromine, and iodine, right? Chlorine has 3 electron shells, bromine has 4, iodine has 5. So iodine is probably the strongest acid of all 3, hydroiodic, because it is so easy to let go of those hydrogens, right? Because they're way far away compared to being really close. So if you know the 7 strong acids, all other acids are weak. And there's lots of them. So if you simply memorize those 7 as being the strong ones, then everything else is weak. This is one you use a lot in lab, nitric acid. Sulfuric is also one you use a lot in lab. Those are the 2 that are hard to remember, chloric and perchloric. So, oh yeah, it's stuff we use in lab a lot. Nitric, sulfuric, hydrochloric, the other halogen acids, and then the other 2 that are harder to remember. So strong acids are strong electrolytes because they dissociate completely. Well, guess what? The rule also works for strong bases. Strong bases are also things that dissociate completely. But now, strong bases dissociate into what? They don't give up hydrogen ions in a nonmetal. What do bases dissociate into? Hydroxide and what else? Whatever the metal is, right? Whatever the hydroxide is hooked up to, whatever the metal it is. All right, there's a trick also for knowing the strong bases. Let's see, there's how many? 1, 2, 3, 4, 5, 6, 7, 8. If you look at the periodic table, and how are yours, Kiko, since you're sitting in the front row. If you look at the periodic table, look here. All right. Any of the alkali metals hooked up to hydroxide are strong bases. That's pretty easy, right? Any lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide are all strong bases. Easy to remember? Yep. Okay. The heavier of the alkali earth metals, meaning calcium, strontium, and barium, are those that make the strong bases. How come beryllium hydroxide and magnesium hydroxide are not strong bases? And it's the same reason that hydrofluoric is not a strong acid. Why are those not strong bases when the other three members of their family are? What's different about these two? It's harder to take away the electrons, but they're also smaller in comparison to the other members of their group, right? Calcium hydroxide, strontium hydroxide, barium hydroxide. The hydroxide that's hooked onto those three things is going to be much further away from the nucleus. It's going to be easier to pull it off, right? These are going to have the hydroxide hooked much closer to the nucleus. It's going to be much harder to pull off. So that's why these are strong acids, these are strong acids. It's easy to dissociate them. Here's a little aside for the strong acid thing, right? We decided that the majority of the halogens, chlorine, bromine, and iodine, make strong acids. The fluorine, hydrofluoric, is the only weak acid amongst them. My favorite TV series is Breaking Bad. I'm sure you guys all know why, right? The chemistry teacher Walter in consortium with one of his ex-students decided to make methane. And there are special brand of methane that is already super pure and something. If you remember, towards the end, I think it was the first season, towards the end of the first season, Jesse was going to sell his house. And they had a bad guy in the basement that he killed. Okay. How do you get rid of the bad guy's body? Walter told Jesse, go down to Walmart and get plastic. And remember, he told him how to have a certain symbol on the bottom of the plastic that was a very resistant type of plastic. He told Jesse, you got to go find a container that's big enough with this certain symbol on the plastic on the bottom of the container and bring it back here so we can get rid of this bad guy's body that's in our basement. Alright, so Jesse goes to Walmart and shows the cameras in Walmart. He's getting into the containers to see if they're big enough to put a body in. I thought that's hilarious. You know? I mean, if you're a bad guy and you go buy junk at Walmart, they watch forensic files, that's how they catch you doing that. So anyway, Jesse's in Walmart. He's trying to step into these containers and said, you can't find one that's big enough, right? He's like, what am I going to do? I can't find one with a special symbol that's big enough. So he goes home, he's trying to think about it, because they want to take the bad guy's body and dissolve him in hydrofluoric acid. So Jesse goes, well, I can't find this container. So he looks around the house and he goes, well, you're in your bathtub on the second floor of the house. That's got to be fine, right? You know, a bathtub is stronger than plastic. So we'll just put the dead guy in the bathtub, fill it with hydrofluoric acid. He'll dissolve slowly with hydrofluoric acid. Okay, well, what Jesse didn't know was hydrofluoric acid will sure dissolve the bad guy slowly over time, and dissolve the body slowly over time. It just turns too much, but also dissolve, of course, from the bathtub. And the realtor came in with a bunch of people and was showing the house. And did you watch that episode? What happened? The bathtub with the dead guy on the floor went all over the floor, so they're showing the house. Okay, so that was a potential disaster. You know, to resell the house, you got hydrofluoric acid and dead guy juice all over your house. That's going to be a little bit of a damage for the new buyers. But hydrofluoric is a weak acid. It doesn't mean it can't hurt you. You take a bath in hydrofluoric acid, that is a bad thing. It simply means that it works over time and it allows equilibrium. So some of them will dissociate and dissolve the body as those ions that are dissociated and dissolve the body are used up, then more are generated from the original hydrofluoric acid, so it will dissolve it slowly over time. So like, if you do hydroiodic,
will that react more violently than the ones that
quicker. But that's not necessarily what you want to do if you want to get rid of the dead body. Right. Because these reactions are very exothermic and a lot of heat is generated. It's better to do it slowly over time than to do it all at once. Right? Okay. If you're a cabinet forensic files, it's interesting, right? I always love to watch forensic files and see what kind of chemistry
Okay.
Hang on just a minute. I'm not good at multitasking. I need to do this.